much for coming to this particular session. And I would also like to thank the Korean water industry and Water Korea for holding such a great session and allowing to be assembled the experts that we have here today. I'm going to talk a little bit about the next generation of hazard resilient infrastructure and concentrate in the process on pipelines. The topics that we're going to cover involve this next generation hazard resilient pipelines. And we'll start with understanding that when we have a soil structure interaction between the pipeline and the surrounding ground, that the actual ground that is started in this process is not the ground that ends the process. You end up with what we call a lot of geometric discontinuities in the ground. You'll get shear bands, you'll get voids and cave-ins, you get different concentrations of cracks, and those all contribute to the deformation of the pipelines that are buried in the ground. When we build a network of pipelines that are able to adjust the ground deformation, we focus on that geometric characteristic. In other words, we fight fire with fire. We try to create a pipeline that moves as the ground moves, and therefore becomes a shapeshifter with respect to the movements that are imposed on it. We've done a lot of large-scale testing. Brad Wham is here, or he'll talk about large-scale testing. There are facilities that are existing now. We started some of this process at Cornell University, and that allows you to look at the large-scale behavior of different facilities that are underground. For example, we looked over here at pipelines. This happens to be ductile iron pipelines and their ability to accommodate ground deformations by virtue of special joints. We have a facility over here that looked at a protective enclosure that is now used for the San Francisco Public Utilities Commission for the Bay Division Pipeline number 3 in the South Bay of San Francisco. We look at a comprehensive testing protocol. We look at tensile coupon tests, which are important to characterize material behavior, the tension and compression direct pulls, direct compression, bending deformations, axial resistance, where we actually pull the pipeline with respect to the ground and get an interaction between the ground and the pipeline longitudinally. And then, of course, finally, in terms of a large-scale rupture test for the actual performance of the pipeline being intersected by a right lateral or left lateral fault displacement. We compare this ground deformation to earthquake-induced ground distortion in what is probably nature's largest life-scale deformation, which was the Christchurch earthquakes of 2010 and 2011. When we looked at the Christchurch earthquake, they took high-resolution LiDAR measurements before and after the earthquake, and therefore you could get the tensile strains or the compressive strains or the angular distortion. That's a deformational metric with respect to rotation of the joints and rotation of the pipelines. This happens to be a cumulative distribution curve that samples about 3.2 million locations in Christchurch that allows you to look at the tensile strains that are captured there as a function of the frequency of occurrence. And if we are to take the test results from places like Cornell, we can characterize them in terms of amount of tensile strain, amount of compressive strain, and you can plot them with respect to the exceedance levels. And therefore you get a systems perspective rather than an individual pipeline perspective. That is, if you adopt a particular type of next generation hazard resilience pipeline that has certain characteristics which you can quantify, then you can go back to a Christchurch and say you exceed, you're able to accommodate 90% of the movements based on the damage that occurred there. And that's really some of the worst damage that we've seen. So we actually are able to tie our observations into actual performance and deformations that have been measured in the field on actual systems. All of this goes onto a website. So everybody in this room has access to reports that have been prepared for at least 10, 11 different companies that have actually characterized the performance of these pipelines and so forth. So you can judge for yourself what's most appropriate. I think they have one also at the University of Colorado at Boulder, and there's one that's available with respect to Berkeley. So you have the ability to gather this information directly right now. We've really looked at an entire ecosystem of different types of pipelines. We have ductile iron pipelines that accommodate deformation because of joint movement. We have polyvinyl chloride pipelines that are able to accommodate deformation because of movement, but also because of stretching of those pipelines. And then we have linings that are actually installed inside active pipelines. And those linings are to enhance the day-to-day performance, but you actually get a seismic or you get a permanent ground deformation dividend. By the way, it's not just seismic. We do look at a lot of seismic, but you have hurricanes, you have subsidence, you have construction activities, you have expansive soils, you have growth faults, you have all sources of permanent ground deformation that a utility would want to consider with respect to being able to design for these large deformation cases. You can see over here is a test where you see the flexibility of one of these polyvinyl chloride pipelines. Well, that flexibility actually affects the longitudinal as well as the circumferential or cross-sectional behavior of the pipeline. And you can see with respect to this slide over here that you have multiple buckles that occur because it becomes flexible, and that allows you to move in compression deformation. You can see where the actual spigot moves right by the bell here, and you can see the pipeline, one pipe moving inside the other. So some of these vinyl chloride pipelines have almost unlimited compressive capacity. And this happens if there's moments on them and even if there's constraints that are on a particular joint. This is a harness that is used in some polyvinyl chloride pipelines. And you can see that when the actual harness makes contact with the bell, then the deformation is over and there is a damage that's imposed on the pipeline. Well, nowadays, we have the ability to look at various ways of connecting pipes, and we have some of these fittings that are able in polyvinyl chloride pipelines to take deformation, both in compression and tension. So you can see here that you can take compression movement or you can take tension movement. As you pull a pipeline out in tension, there are these teeth that actually grab onto the pipeline that's placed in the fitting, and that creates some force capacity. And over here you have some tension tests that have been performed. The important thing is that this is a very flexible connection, and that allows for up to 3 to 4 inches of movement before there becomes some loss of water and leakage in the pipe. So these particular connections have real capacity for deformation. And then over here, you see in the compression where there's a sliding until you hit this ledge, and then there's a buildup of deformation and then a very abrupt failure as you crash through this particular ledge. So you have capacity in these kinds of fittings that is able to take up large amounts of ground deformation. I think this is a real breakthrough in terms of being able to put together strong and resilient systems. Here's a picture of some deformation and bending going on with the polyvinyl chloride pipeline. And you can see that you get almost 45, 50 degrees of deformation that imposes itself on one of these joints. This is a perpetual buckling pipeline, where you actually have a buckle that forms and it continually develops compression at one particular location and is very well set up to take compressive deformations. You see over here that if it's imposed to longitudinal deformation in this direction and you have an offset imposed on it, you have a double loss or additional capacity in terms of compressive deformation. So these joints can buckle, they also can rotate, they allow for the geometry to be maintained. This is the inside of the pipelines. You still have about 90% throughput in terms of some of this deformational capability. And then, of course, there's linings. There's cured-in-place linings, and there's cured-in-place pipe. The difference between the two is that a lining is more of a balloon-like material, and a cured-in-place pipe is an actual structural pipe that's lined inside a pipeline and will act to be able to accommodate deformation at abrupt fault displacements or abrupt displacements associated with other sources of ground deformation. We learned a lot from this testing process. For example, when you have a pipeline that is lined with a cast-in-place liner, so it's a flexible liner. When you have shaking in post-on, so you have an opening and closing of vertical joints. If you open that joint far enough and you have a pressurized lining system inside the pipe, it will actually protrude, and the next cycle of compression will guillotine off that particular lining, and that's the failure mechanism. So we never knew this when we first started to do these tests. It was something that we learned in the process of doing it, and you can create models where you actually can show that the crack or the joint opening is going to be a function of the peak ground velocity and the pulse period. The pulse period is mostly in periods of less than 0.2 seconds. So most of the behavior is going to be focused on the peak ground velocity. And for these types of linings that we looked at, they begin to break up. You have the joint openings at about 200 centimeters per second.
Excuse me, Professor. For translator, want to get the microphone.
Oh, sorry. Okay, so when you look at cast-in-place pipe, you actually have the capacity in some of these fault rupture tests. You can see that, the lining extrudes as you are subjecting the pipeline to tension, and this maintains the continuity of flow and the ability to accommodate deformation. Okay, so lessons with respect to the next generation of hazard-resilient pipelines is that, number one, it's a paradigm shift for pipeline technology. It becomes a market-driven research which is funded by the industry. We helped to commercialize and test about 10 new pipeline systems, and this becomes a contributor with respect to bidding on future jobs. So you really can't have resilience unless you have a market, and this allows for different products from different manufacturers to be put into the system, and therefore you have a selection of hazard-resilient pipelines. Okay, the next topic is we learned a lot during these testings with respect to answering basic questions about deformation and developing simplified models that can actually account for some of this movement ahead of time. One of them is the actual resistance of pipeline joints. We actually were able, through people like Artem Studlein, who's up here, he's at Oregon State University. He wrote a paper where he referenced some of the original German work of accounting for protuberances that extend beyond the radial dimension of a tunnel or a pipeline. These are very difficult to characterize. He was able to show that those worked for certain types of pipelines. We adopted this particular procedure. And basically, you're able to define a dB diameter and a ds diameter, and you have this relationship line that we show on the left, where you have resistance in terms of longitudinal resistance that gets developed in these lines. And if we take some of the actual data that we acquired with respect to restraints, with respect to bells that are enlarged because they accommodate large amounts of deformation in ductile iron pipelines, but we very rarely take the protuberance of these bells into account. What you get is a cross-section like this. You have these dimensions. When you plug this in and you take the very experimental data that we have, you plot the measured displacement with respect to predicted load drop, you have an extreme good fit with respect to the actual data. So you actually have solved a major problem with respect to protuberances around cylindrical types of facilities like pipelines, and actually can account for enlarged bells and can account for constraints, which we weren't able to do before. So then I'd like to talk and finish up by talking a little bit about the topic of pipeline intelligence. We were able to work with a number of different people. One set of people that we worked with were Cambridge University and the University of California at Berkeley. We looked at joint movements and bending strains and so forth. Right now, under the direction of a professor by the name of Kenichi Soga, there are fiber optics, distributed fiber optics that are being applied to various pipelines that cross the Hayward Fault, which creeps, and therefore they provide a monitoring system for the accumulation of strain and the potential for failure of some of these important transmission pipelines. So you can see them going into place. These happen to be high-density polyethylene pipelines that are crossing the fault, and they're providing an active measurement system for the different utilities. There's data or sensing that's called time domain reflectometry, and that's able to measure different changes in the water content of the ground, so it actually tells you when you're getting leakage. And the most important part of it is the development of a wireless network to be able to communicate this information outside of the ground to a receiver station, and that data to be able to be collected and to understand what it means with respect to the difference in strains and deformations that are imposed on the pipelines. So, again, you have this paradigm shift in pipeline technology. You have market-driven research, which is funded by industry. But in this case, you can't have resilience until you have intelligence. We could put the best intelligence that we have of pipeline systems in the ground today. And we can be pretty well assured that we can accommodate large ground deformation with these hazard-resilient types of pipelines. But 20 years from now, some of these pipelines they're not going to be any smarter than they are today. But what people are beginning to find out about pipeline networks is they are excellent conduits for sensing systems, for fiber optics, for all kinds of data gathering that not only allow you to understand the real-time performance of the pipeline system, that not only allow you to understand what the pressure is, what the elevation is at various locations, and create hydraulic networks that truly reflect what's in the actual pipelines, but also to sense the environment and see what is happening in locations that are very close to these pipelines. These pipelines fan out and define our urban infrastructure. And what's beginning to happen is you're beginning to use these pipelines as conduits of information and data gathering about the behavior of the system and about the behavior of things close to that system. So, Barbara, you started with these nice conversations, and you said, what are the pipelines of the future going to look like? Well, one possible reason, or one possible answer to that, is to have a network of sensors in these pipelines. I actually believe that 20 years from now, the cost of sensors are coming down, things are being imposed in these systems or being built into these systems, and they will become major conduits, not only to carry water, but to carry information, which becomes the new oil with respect to defining the urban infrastructure. Finally, I'd like to say that the next generation of hazard-resilient pipelines, pipelines that are shape-shifters, that can accommodate ground deformation, is not only a good practice, but it becomes a culture. People around the world who operate pipeline systems and the customers that are serviced by the services that are provided by the systems are beginning to expect that you're going to be able to tolerate ground deformation, are beginning to understand that these are natural conduits for sensors, and they're wanting these systems to behave with the highest technology that we can provide for them. So I think that's my last slide. It is, and I'd be happy to answer any questions. I think we're on time.